So welcome, and we're going to start talking about heat and temperature and internal energy and specific heat and expansion and various things. So the important thing with this section, I think, is to take care of the basics, and then the other stuff will take care of itself. People, speaking for myself, I made more mistakes on this because I didn't really know what the difference was between one thing and another. It wasn't clear. I knew how to use them in sentences, but I never really stopped and thought, what is this thing? So we've got to have a few definitions sorted out. And so the first three that come up the most often are the difference between temperature, internal energy, sometimes called thermal energy, and heat. And it's really all about internal energy. When you put energy into a substance, if it's a solid, the stuff vibrates more. If it's a liquid, it travels faster and collides more. If it's a gas, it travels faster and hits the walls of the container more. So the energy that you put in is stored as kinetic energy inside that substance. And we call the energy inside the substance that's caused by this as internal or thermal energy. So you're thinking about the vibration of solid atoms, or you're thinking about the whizzing around of liquid atoms or gaseous atoms. That's internal or thermal energy. If I touch a substance with a lot of internal energy, it may or may not be hot. If I touch a substance with a little bit of internal energy, it may or may not be hot. Temperature is not a good measure of how much internal energy is in something. Temperature is a good measure of the average energy per particle, the average kinetic energy per particle. So I can have a teaspoonful of boiling water, and it's got a very high temperature. But it's not got that much internal energy because there's not a lot of it. And I can take a big ice cube, which has a low temperature, but it's got a massive amount of internal energy because there's a lot of it. And that's where we tend to make our first conceptual mistake. We think that things that have a lot of internal energy must have a high temperature, and things that have a high temperature must have a lot of internal energy. And atom for atom they do, but we're not necessarily comparing atom for atom. So there's a difference between temperature and internal energy. And if I say that internal energy is the sum, I'm sorry, I always do that, and then I go back and put my pen on. If we say that the internal energy is the sum, the addition of all the particles' energies, so if you have 5 particles, I have 5 things added together. 1,000,000 particles, 1,000,000 things added together. Temperature is the average kinetic energy of the particles that make up the object. So take the total amount of energy and divide it by the number of particles, basically. So if it's got a high temperature, those particles are moving like crazy. And if I have a lot of them, I've got a ton of energy. But if I've only got a few of them, I've got less energy. But they're moving like crazy. And if it's a lower temperature, then those particles are not moving so much. If you've got a lot of them, they might add up to a fair amount. But if I only have a few particles, there's not so much of it there. So I've got to distinguish in my mind between average energy per particle and total amount of energy, if you like. And a good analogy would be Bill Gates is very wealthy because there's one of him and he's got a ton of money. As a country, the rest of us actually are not very wealthy on average, but we have more money than Bill Gates does. There's 300 million of us. So individually we're not very wealthy, but collectively we add up to a lot. So individually, that's like our temperature. And collectively, that's like the internal energy. Okay? So Bill Gates would be like the teaspoon full of hot water, and we'd be like the iceberg full of ice. Yeah? But there's more of us, so collectively we have more money than he does. Maybe not by much, but we do. We have more money than he does. And then heat. So a common mistake is people will talk about how much heat is in that object, and we don't. We talk about heat as being the energy in transition. So when I put the spoonful of boiling water onto the ice cube, then heat flows from the spoon to the ice cube. Heat always flows from a high temperature thing to a low temperature thing. Okay? It's weird that we have a different name for it, but we do that. For instance, my college has money in its bank account, and I have money in my bank account. But when they're paying me, they call it my salary or my wage. We give a special name for it when it's in transition. It kind of makes it distinct from what's in their bank account and what's in my bank account. Once it goes into my bank account, it just becomes money in my bank account. It's not special. It's all salary originally. But I give it a special name when it's in transition. And that's what I do with heat. Heat is energy as it's transferring from a hot object to a cold object. And then the next question is, why is it always transferring from a hot object to a cold object? And I can kind of show you that by basically, if we imagine a row of particles, and these are part of the ice cube. And then I have some more particles. Let me change colour of my pen, actually. Then I have some more particles. Let's go to ink colour. Let's go to black. Let's have some more particles. And these are the particles of the spoon, if you like. And what happens is initially is that these particles are all bouncing around about the same extent. And these guys aren't. Now, the black particles don't know there's only 3 of them, and the red particles don't know there's, well, let's do more red particles. The red particles don't know that there's, I'm not going to do 1,000 of them, but there's a ton of them. There's like so many. It goes on forever. They don't know. All they know is I'm in this place, and there's a particle to the left of me and a particle to the right of me. And these guys are all vibrate a little bit. They all vibrate the same because they're at the same temperature. It's no big deal. And even though if you add up all the energy here, the energy there is more than the energy there. Even though the 3 little guys that are moving like crazy have more energy than the however many it is red guys. In fact, these 2 guys, if I look at, I'm going to do this again, I'm sorry. It's just I want it to be as clear as I can make it. If I look at these 2 guys, the first red one and the first black one, they're not balancing each other. So what happens is the black one on the right jostles the red one, kind of drags it along with it. And so over time, the red one starts to vibrate a bit more, and the black one vibrates a bit less, because they're trying to get balanced with each other. And then this first red one now starts making that other one balance, jostle a bit more, and that makes these guys go a bit less, and then that guy goes a bit more, and these guys go a bit less. And so eventually, they all go a little bit more than they used to go, and they're all in equilibrium again now. So it's done particle by particle. So when I put a spoon in contact with a huge iceberg, it doesn't know I'm part of an iceberg. It just knows that guy's vibrating more than I am. And I'm going to get energy from it, and I'm going to vibrate more. So the 2 particles go to the same temperature, and then the next 2 particles go to the same, not immediately, but, you know, the tendency is they go to the same temperature. That's why the heat flows from the high temperature to the low temperature, rather than where there's a lot of energy to where there's a little bit of energy. Okay, so can you see how it's a bit confusing? I mean, these guys originally, they didn't know about atoms. It was only Dalton who brought in the idea about atoms. So what did they do before? They knew if you put your hand on a fire, it got burned, so they wanted to talk about it. And so they had this idea about this caloric fluid, and things that were hot contained a lot of this caloric fluid, and caloric fluid would flow from a hot thing to a cold thing. So as your hand heated up, you are gaining caloric fluid. It kind of works. Problem is you're then going to go looking for this caloric fluid, and you can't find it because it doesn't exist, you know. But you're going to look for it. So, all right, we know about temperature. We might not know what it is, but we know hot's hot and cold's cold, say, before we knew about atoms. You knew about temperature. You want to measure it because if you touched the wrong thing, you burned. So we've thought of any way we could find a measuring temperature. And I don't have the most classic way, actually, ironically, man. The old thermometer, the glass tube thermometer that I'm sure you've all seen. They used to be silver because it was filled with mercury, and they stopped doing that. And then they were red because they were filled with alcohol, which had a few drops of colour dye in it. Oh, that was okay. But these days, we don't even use those so much because they break. So now we'll use anything we can that changes a property with temperature. So one of the first things they found was there are some metals that generate a little voltage as the temperature changes, so we use those. They were thermocouples. And some metals whose resistance changes with temperature, and so we can use those as well. Anything we can do to get a little electronic thermometer, we'll use it. I'm going to change colour pen because this one doesn't show up that good. So we'll use it. So that's a great thermometer. And there's other ones. This is a piece of metal that coils around. It's actually two pieces of metal joined together. It's called a bimetallic strip. And as we'll see in a minute, if one of them expands more than the other as it gets hotter, the tendency is it tends to twist the thing. So get those two and coil it and put a needle on it. And then as this thing coils and uncoils, this needle's going to go backwards and forwards. And here we have like a weather vane, like you might have in your garden, one of those temperature things that you put outside. If you look at the back of it, you can actually sometimes see the coil. We just leave the coil there. Well, that's okay. It's a little bit crude. It's not that good. This is in a way, the better way, certainly if you're dealing with very high temperatures or the like. If you put a piece of metal into a furnace, it might melt. But you can actually look at the glow from the furnace and get the temperature. And so you find you get these emission of radiation, the light-sensitive thermometers, just because different temperatures have different colors that they glow at. Okay. We see light that's reflected. The sun glows with all these colors, and we see that reflected light. If we turn all the lights off, it's tempting to think that there's no glowing. But there is. There's temperature, so there's glowing. The only thing that doesn't glow is absolute zero doesn't glow. So you can see these colors and you can identify them in terms of what's going on. So an infrared camera, for example, would be this kind of thing. People found when they did work on liquid crystals, like your calculator. If you have a calculator that has the display, the numeric display that's not light, it doesn't glow, it just like reflects. They're liquid crystals. And when people played around with those, they found that they were temperature dependent. So you can actually get these little strips of like film, and you put them on your baby's forehead, and it glows with the color. The brightest color is the temperature of your baby's forehead. So you don't need to do the thermometer trick anymore. You can just do it like that. It's not quite as precise, but it's pretty good. And then, in fact, it's funny actually. So my brother sent me, when we had our baby, my brother sent me that across. And I've never thought to look in the drug aisle. Can you get those in the States now? I'm going to look in the CVS or something like that, because I don't remember seeing them. But because my brother made a big deal about, oh, you got a baby, you need this thermometer. It's really nice. So I've got to check to see if we have it. This last thermometer is what they give to people when they retire. They used to give clocks. When my granddad retired, they gave him a clock. And he put it on a cupboard. He put it in a cupboard and basically he kept it for about 2 months. It was a gold thing. He put it in the cupboard, and we never saw it again. He brought the old one back out. And my grandmother said, "What's up? Did your clock not keep good time?" And he goes, "I don't want a clock for my retirement. I'm counting the seconds until I die, you know." So it became bad practice to give people clocks when they retire. So now they give them thermometers. So like, I don't know. It's like, I can't think of anything else to give you, so I'm going to give you a thermometer, you know. And it's a tube, and it has these little bubble things in, and they go up and go down. Anything that measures temperature, they'll use as a thermometer. Anything. All right, but that's fair enough. But then what scale are you going to put on? Are you going to have the Bonaquisti scale, which would be really nice, but no one else uses? Or would it be, you know, the Fahrenheit scale, or would it be the centigrade scale? Well, Fahrenheit was the first person to come along. And what they did was, so Fahrenheit was interested in medicine. So he wanted the human body to be at 100 degrees. And then he basically made up a brine bath, because what you need is so you have a length of tube, you know, and you want to mark one of it as one point, and then you heat the thing up and you mark the other one at the other point, and then you divide all the points in between, and there's your temperature scale. So he used 100 degrees Fahrenheit for the body. And then he'd made up a brine bath. He put ice and salt in a bath to get as cold as he could. And he called that 0 degrees C. Degrees F. Well, just ice water would be at 32 degrees F. This is ice water. And boiling water would be at 212 degrees F. But he didn't care. He wanted human body to be about 100 degrees. And he made it pretty much. I mean, it's pretty close to it. Problem with that scale is it's a wacky number for boiling water and a wacky number for ice water. And also 0 degrees doesn't mean no average energy per particle. Maybe 25 years later, along came Celsius. And Celsius is not interested in biology. He's just interested in science, well, physics, I guess. And he puts this into ice water and calls that 0 degrees C. And he puts it into boiling water and he calls that 100 degrees C. So this is ice and this is boiling. And it's nice because we have 100 divisions, and we like 100 divisions. And anybody all over the world can check it. You just put it in ice water, you put it in boiling water, and you're done. You don't have to worry about, has this person got a fever or not got a fever or whatever. So for the longest time, the Fahrenheit scale was what was used colloquially in the street. People would use the Fahrenheit scale. And the centigrade scale was what was used in science labs for the longest time. And then there came, and the other problem with the centigrade scale is that 0 degrees centigrade does not mean no average energy per particle. But they work. And differences are differences. So if you want to measure how many degrees something gets hotter, you can measure it. If you want to set the oven to bake bread, you can set it. It works. It's pretty good temperature scales. Britain now has gone to centigrade scale for everything. Britain now uses centigrade scale. United States is one of the last countries to use Fahrenheit scale for temperature. In colloquial days, not in science, but outside in the street, we use Fahrenheit. Problem with both of them is 0 is not no average energy per particle. And in about 1850, we've already got steam engines. The Industrial Revolution is already going on. A guy called, he's finally called Lord Kelvin because he got raised in the British aristocracy. He was like I think he was pretty well to do before he began, but he became a Lord Kelvin. Lord Kelvin said we need to find the temperature of absolute zero, as cold as it can get anywhere in the universe. That's ridiculous. How can you, I mean, how are you going to do it? Take your thermometer to, the backside of the moon or something? How are you going to do it? And you don't need to do it. What you do is you find the pressure of a gas cylinder at melting point of ice, and you find the temperature, you find the pressure of the gas cylinder of boiling, of the same gas when it is in a bath of boiling water. So you're not putting, you've got this gas full of nitrogen, say, and it's got a little pressure gauge on it, and you measure the pressure when it's in ice, and you measure the pressure when it's in boiling water. And you put down those two pressures, and you put down those two temperatures, and you assume, and it's a fair assumption, that at different temperatures, and you can check it, you go to mid-temperatures, and you find you get a nice linear expression, that the pressure changes linearly with temperature. And if you work it, you can go to dry ice. And these days, we can go to liquid nitrogen, and you find you get a nice straight line, and it points down to here. When there is no pressure because the gas particles are no longer pushing against the side of the vessel. They're just laid at the bottom of the vessel, all tired out. Okay? When there's no pressure, you come down to minus 273 degrees C. And Lord Kelvin said, let's call that 0 degrees. And we'll measure upwards from there. So melting ice is not 0 degrees, but it's 273 degrees. And boiling water is not 100 degrees, but boiling water is 373 degrees. And they decided to call this after Lord Kelvin, so we call these K. That's where the Kelvin scale comes from. It's the same size of degree as the centigrade scale. We're just changing the starting point. And the big advantage of this is that when I double my degrees Kelvin, I do double the amount of energy per particle in my object. When I double my degrees Celsius, that's not true. When I double my degrees Fahrenheit, that's not true. So if I think about it, I can double the volume of something and I know exactly what I'm doing. I can even double the pressure of something because I can measure pressure from 0. But I was never able to double the temperature of something and know what I was doing because 0 wasn't 0. But now with the Kelvin scale, 0 is 0. So it's amazing, a major leap forward. And it only happened about 160 years ago. It's a major leap forward. Early thermometer scales, that's the Fahrenheit and the Celsius scale, did not know the temperature of absolute 0. Absolute 0 corresponds to no translational kinetic energy per particle, and that causes no gas pressure. And science likes absolute 0 because not only is it in principle important, but also as you get closer and closer to absolute 0, thermal effects become less important on materials. And so some materials behave really strangely. Like some metals have absolutely no electrical resistance. Some fluids flow and they coat surfaces. They don't worry about gravity at all. So we can get helium-1, helium-2 and all that. You get some weird, very strange stuff going on. And even though people... So how close can people get? They can get within 1,000th of a degree of absolute 0 in a real refrigerator. The refrigerator is as big as this, well, not this room, but the refrigerator will be as big as that doorway, and the sample size will be about the size of your thumb. But they can get it as cold as that. They can get really far down so they can study these materials really carefully. And they'll learn a lot of physics from there. From an engineering point of view, that's a lot of effort to get one little bit really cold. But these days they've managed to make some so-called ceramic superconductors. Through studying using machines like that, they were able to learn more and more about materials, and so they were able to guess that these yttrium, barium oxide materials would become superconducting at relatively high temperatures. And so there's this race on to get these weird effects to occur at higher and higher temperatures, because although absolute zero is incredibly hard to get to, both technically and also in terms of finances, liquid nitrogen is pretty cheap. So if I can make something that superconducts at liquid nitrogen, which you can now, then you can have relatively cheap superconducting magnets. So it's very interesting. Engineering then becomes relevant. Okay, so temperatures measure the average kinetic energy per particle, and now we know how to measure it in real terms. In terms of zero is zero average kinetic energy per particle, and you know, if I double my temperature, I've doubled the amount of energy per particle. So that's great. What about heat? So heat is the energy that transfers because of temperature difference. Energy does not transfer because of a difference in the amount of energy. So here's I just told you about this. The teaspoonful of boiling water and the iceberg full of cold ice. And sure enough, the heat goes towards the cold ice because it goes from hot temperature to cold temperature, not where there's a lot of energy to where there's a little bit of energy. So that's a kind of weird thing. And then internal energy and internal energy, or sometimes called thermal energy. A body does not contain heat, it contains internal or thermal energy. It's all measured in joules. Heat's measured in joules. Internal energy is measured in joules. It's just when we're transferring it, we call it heat. Internal energy is the grand total of all the energies. So we have translational kinetic. That's the thing vibrating around. Rotational kinetic is it spinning. And then we have internal potential. Is there kind of like stretching or a straining between the particles. So three obvious ways we can store energy. Some of them are more important for temperature than others, it turns out. When a substance absorbs heat, internal energy of the substance increases. If your temperature goes up, your internal energy goes up. Took me a long time to get that. It seems sometimes the textbooks deliberately don't tell you things so they can ask you questions about it. And for me, studying this thing was this realization that you got to know what the words mean, and then you got to sweat the details about when this happens, what does that mean for heat and temperature and the like. So when a substance absorbs heat, we put a fire underneath it. The internal energy, the temperature, well, the internal energy of the substance increases, and as temperature is the average energy per particle, assuming I'm not losing or gaining any particles, then the temperature follows the internal energy, and the internal energy is dependent upon the heat. So, when a substance evolves heat, that means gives off heat, internal energy of the substance decreases, and if we don't lose or gain particles, my temperature should fall. Sometimes a substance can use heat to change phase. That just means it goes from solid to liquid, or it goes from liquid to vapor, or, frankly, from solid to vapor. We can sublime, which means we go from solid to vapor, or backwards. We can go the other way. Instead of changing temperature. So most of the time, when I put heat into a substance, it gets hotter. But every now and then, I get to this stage where it starts melting or it starts vaporizing. Okay, the SI unit for heat, well, it is the joule. It's the same as work. Why is it the same as work? Because it is the same thing, it's energy. How do they know? Because Joule, ironically, it was named after him, but Joule on his vacation went to the Alps, and there's all these waterfalls in the Alps, and he measured the temperature near the top of the waterfall, and he measured the temperature near the bottom of the waterfall, and he looked to see the temperature change, and sure enough, there was a temperature change. The water was hotter at the bottom than it was at the top, and he figured out the change in work is delta W, and he looked at his change at temperature, delta T, and he figured out that the amount of heat that went into the substance was the same as the amount of work that was done by the falling water. So it all worked out, and it was like great. So now we know that heat should be measured in joules, but we didn't always know that, and we've got the tradition. So, for instance, if you go to the store and you buy candy bars, you will actually see that. Calories with a big C. It's not the same as calories with a little c, and that's confusing. If I take... let's see if I can remember it actually. If I take a gram of water and I heat it up, I should know this, I'm so sorry. If I take an amount of water and I heat it up from so many degrees C, no, I'm giving you the... Yeah, but raise what 1 degree? That's what I'm struggling with. Anyway, it's 1 kilogram by 1 degree C. Yeah, that is a calorie. And if I measure it in pounds of water and 1 degree F, I get the British thermal unit. Very direct ways of measuring heat. They don't have to know that there's atoms. You just need to be able to measure things. There's a relationship between these, of course, so we can get to that. And then along came the food industry. I'm being a bit cynical here. I don't know that this is actually 100% true, but I think along came the food industry, and they said, man, our Snickers bar contains 240,000 calories. No one's ever going to eat that. Well, how much do you think they'll eat? Well, we'd eat a couple of 100 calories. So they said, let's invent the food calorie. So 240 big calories. And so that's where the big calorie comes from, the food calorie. And sometimes put down food calorie, but sometimes just put big capital C-A-L, which I kind of think is cheating. Because people get these confused all the time. You know, you got to watch out for that. Okay. So in-class check, temperature is a measure of, what do you think it is? Shall we have a go at it? Let's, if you got a clicker, click. So what is temperature a measure of? It's a measure of how tall something is. Oh, what do you think? 1, 2, 3, 4, 5, 6. Okay, almost there. Anybody else want to go? Okay. So it's going to be a measure of the average translational kinetic energy per particle. I'm not going to play a game with you and put down the average kinetic energy and the average translational kinetic energy. It's just sometimes I'm being more specific than I am other times. So on a test, don't worry about translational or not translational. It's the average kinetic energy per particle. Okay. So that's that. If you apply a flame to 1 liter, 1 bottle of water for 5 minutes, and you get a 6-degree temperature rise. I'm asking for your intuition. We've not done this little bit yet. We're going to do it next, but I have a bucket full of water, and I put it on the fire for 5 minutes, and the temperature goes up by 6 degrees C. If I put twice as much on the fire, what do you think the temperature is going to go up for? Again, for 5 minutes. Do you think it's going to be a higher temperature or a lower temperature? What do you think? What's your intuition tell you? So I want to know, how many degrees is this? It's on for 5 minutes in both cases. Same fire. So what do you think? It's either going to be a hotter temperature or a colder temperature or stay the same. What do you think? Twice as much stuff to be heated up. Same amount of heat. Because same fire, same length of time. Twice as much stuff to be heated up. Same amount of heat comes in. What do you think? Average amount of heat, average amount of energy per particle. We're kind of heading there, aren't we? Let's stop it. So most people saying, yeah, what happens is you get the same amount of heat and it's got to raise the temperature of twice as many particles. And so it does it half as high. So it's going to be that. And then an iron thumbtack, a little thumbtack, and a big iron bolt are removed from a hot oven. The oven gets them to a same temperature. Ovens go to a 400 degrees C. They stay at 400 degrees C. You put the tack in, you put the bolt in. It's got 400 degrees C temperature. Yeah, you let them get there. Both are red hot. Each is dropped into cups containing equal amounts of water. Yeah. Okay. So here's my little thumbtack. And here's my big bowl. Okay. Which cup will get hottest? The cup with the thumbtack or the cup with a big iron bolt in it? What do you think? What's your intuition tell you? You got this thing and it's been in the oven. There's more of it. More particles. They're at the same temperature and they're made of the same stuff. So they're going to react to temperature the same way. So which one contains more internal energy? And then when you take it out, which one is giving more of that energy to the liquid? So there's a lot of things going on here. Yeah, let's stop it there. Most people are saying B. Yeah, iron bolt has got more substance. Therefore, more substance, therefore it can transfer more heat to the water. Let's put that into some numerical values here. I can define a thing called a specific heat, and actually as time passes I prefer this to write it down this way. Is the amount of heat, I call the amount of heat not Q but delta Q, over the mass times the change in temperature. And I find if I do that for iron, I'll get one value. I put iron in, I give it that amount of, I take iron, I want it to raise by 1 degree, I have 1 kilogram of it, I find I need that amount of heat to get it to happen. I take aluminum, a kilogram of aluminum, I wait until it increases by 1 degree, I get a different amount of heat. I take brass, different amount of heat. Take copper, different amount of heat. Let's put all those down in a list. Put them in an engineering handbook. And what I find is I can make a table, and I put down just a couple. So copper takes 387 joules to raise the temperature of 1 kilogram of copper by 1 degree Celsius. If I had ice, it would take a kilogram of ice. It would take 2,090 joules to raise the temperature of the ice by 1 degree. Not to melt it. This is minus 10 Celsius ice going to minus 9 Celsius ice. Or minus 15 Celsius ice going to minus 14 Celsius ice. It's a solid just like copper is. It's just that it's now below its melting point. If I took water, the same substance that ice is made of, I would get 4,186 joules. Water is one of the hardest substances to heat up. It's also one of the hardest substances to cool down. It's kind of very stabilizing. When I was a student, I lived in this house that had shared facilities, common hallways, a common bathroom, different rooms off it. It was like a low rent place. And the landlady was not the kindest person in the world. And I got home one day and she turned all the communal electricity off. So no hall lights and no water, no hot water. Apparently we all paid our bill for our electric in our rooms, but the landlady was responsible for the hallways and the shared facilities. So hey, just turn them off and you can save some money. So I really wanted to go out, and I don't know if you know this, but in my generation in Britain, it was only kind of like halls of residence or probably hotels or a university dormitory or something like that would have a shower. All the houses had baths, and that was it. And it wasn't the tradition for people to get bathed that often. Maybe once a week, maybe once every 2 weeks. And it's just the way it was. It was the culture at the time. I've gone back. It's changed. There's a lot more showers around. Showers are very convenient. But, you know, my dad's generation, even worse, my dad's generation, they had to get the bath into the front room because it wasn't plumbed. And they'd pour boiling water on from, you know, a big pot. And, you know, it was like Middle Ages. But that's the way it was. And so people weren't as clean. So why am I telling you that? I have no idea why I'm telling you that. Oh yeah, so she turned off the. I'd run a bath before I realized it wasn't, the sun hadn't set. I'd gone in. I turned the thing on. It was getting dark. I went to do the light switch. No light switch in my room. Going down the hallway, one of my neighbors said, "She's turned the electricity off." Oh no, there's electricity in my room. Going down the hallway to get my bath. "She's turned the electricity off." "What do you mean?" I'm looking. "Oh, the light switch is not working." "No, she's turned it all off." "Oh, I'm going to get a bath and go out anyway." So I get in the bath and it's cold. And I think, oh, I'll just sit here a little while. I am ashamed to say this because I should have known better. I'll just sit here a little while and warm it up. So I sat there for 5 minutes shivering because I'm never going to warm up the bath, because the amount of energy I can give it compared with how much it needs to get it to my body temperature is, I don't have that amount of energy inside me. That's hypothermia. That's hypothermia. That's why people, even in the Gulf, if they fall in, if they're in the water too long, they won't do well because it's not body temperature. Sometimes it feels like it's warmer, but it's not body temperature. So these are useful things. They're very useful in some ways. You want something that's going to warm up quickly? Use copper. So you want to make a cooking utensil? You know, use copper. You don't want to spend 2 days heating up your pan so you can then fry an egg. You want something that's going to heat up quickly, so use copper. You want something that's going to maintain a lot of heat? Use water, ice, concrete, something like that. It's So at the bottom, I've got basically added energy versus temperature for these different things. So we can see it's nice and linear. It goes really well. And that's called the specific heat. It's specific heat because it's specific to the substance. It's per kilogram degree C. Okay. A 3 kilogram sample of yolk requires 90 joules of heat to raise its temperature by 6 degrees. Let's do this together. What is its specific heat? Specific heat is the amount of energy I need per kilogram per degree C. So I have 90 joules, and it was 3 kilograms, and it was 6 degrees. That's going to be 90 over 18, which is 10 over 2, which is 5, I think. 5 joules per kilogram degree C. So that would be that. Cool. Okay. Next, we have this tendency of substances to melt or vaporize, or solidify, or condense as a liquid. Goes either way. Different substances take different amounts of energy, and we say the amount of energy, this should be delta Q, is equal to M times L, where L is the latent heat. Always say our latent heat is the amount of energy you need over the mass. There's no temperature change in this one, because it doesn't change temperature, it changes state. So we say water, look at this, this is a massive number. 1 kilogram of water takes 333,000 joules. If you want to vaporize that water, it takes 2,260,000 joules to vaporize that water. You get all the energy back if you can condense that steam, by the way. It's a wonderful way of storing energy. If you can change water into steam, it's going to take a lot of energy, and you can condense that back. It's going to give you all that energy back. It's really an amazing place. If you have to store energy, try using a change of phase. Don't make things hotter. Make them vaporize. It's great. Copper, not so much. Still a lot. Well, actually, for copper, if you want to get vapor copper from liquid copper, good luck. It's 5 million joules for a kilogram. And then aluminum, 11 million joules for a kilogram. So how much heat is needed to change? So I want to know the amount of heat needed to change. L equals Q over delta M. So how much heat is needed? So delta Q is equal to Lm, which equals water going from ice. So it's that one I want. You don't need to know these numbers. I will always give you them. But have a feel for how big they are. Over, times M, and the mass in this case was 3. So delta Q is equal to 999 joules. So if you want to keep an idea of 1,000,000 joules of energy, vaporize 3 liters of water. Okay, is that right? 3 kilograms, a liter is 1,000 cc. Yeah, kilogram. So 3 liters of water, vaporize it. You converted 1,000,000 joules of heat into thermal energy inside the thing. This is where it gets interesting. I'll just keep checking the time. Yeah. Because things typically start off as solids, and then they melt, and then they become liquids, and then they vaporize, and then they become vapors. So that's the particular pattern. As you put more heat energy in, this is what happens. In truth, you can mess with materials, and you can actually sometimes get a solid to go straight to a vapor. But to do that with a typical material that does not, for a typical material that usually melts to liquid and then goes to vapor, in order to get it to go straight to a vapor, you've got to mess with its pressure to get it to do that. There are other substances like cobalt, which will automatically do it. They'll at room pressure, they'll sublime, it's called. What we're going to deal with, it always goes solid, liquid, vapor. This is all about the latent heat. This first bit is all about the latent heat, and it depends on the latent heat indicates the slope. It isn't equal to the slope, but it's dependent upon the slope, or the slope is dependent on it. And this bit here is dependent upon the specific heat of the water, and this is the specific, dependent upon the specific heat of the vapor. And these bits in between depend upon the latent heat from solid to liquid and the latent heat from liquid to vapor. I've exaggerated the diagram. It should look like this. It should look like that with a massive thing, and then a little bit of that, and then a massive thing, and then up like that. The plateaus are huge compared with the slopey bits, but to make the diagram look okay, we've done the plateaus as somewhat narrow. So here's the thing. If I'm putting heat in, let's say I start here. I'm solid, I'm not at my melting point, and I give you so much energy. You use some energy to stop being a solid. Well, no, I'm sorry. You use some energy to get to your melting point. You used a bit more energy to melt yourself, and then you use what's left over to warm you up. So you ended up as a liquid at that level. So you heated yourself up to your melting point, you melted yourself, and then you heated up the melted fluid. And that's where you ended up. It's always this pattern. In Physics 1, I can give you just the specific heats and the latent heats and let you get on with it. But in this level, we do a bit more holistically. So I can say upon heating 3 kilograms of yolk at 50 degrees C is converted into liquid yolk at 60 degrees C. The warming the solid to its melting point took 25 joules. Now, okay, first thing, this is yolk. So that's not 0 anymore, and that's not 100. But this is still the melting point, and that is still the boiling point. So in order to raise the yolk to its melting point, took 25 joules. And then warming the liquid yolk, warming the liquid yolk to its final temperature took 30 joules. So that bit there, which caused that thing to happen there, that took another 30 joules. It says the entire process took 70 joules. That's the entire thing. So it says how much energy was needed to melt it. So how much energy did I use in that bit? If the total process took 70 joules and I used up 25 in getting it to its melting point, and I used up another 30 in warming up the melted yolk, how much was left over? I used 70 in all, and 25 was used there, and 30 was used there. So that left 70 minus 55. You see that? So that's going to be 5 makes 60, 15. So I used 15 there. If the whole thing was 70, and I used 25 on that bit and 30 on that bit, I used 15 on that bit. Okay? So that's the kind of level we want to get to. Cool. How am I doing? I'm going to stop.